So we're going to take a look at the things that affect the phases of matter. So the phase of a specific substance is going to be determined by multiple things. We've been talking in length about intermolecular forces, but temperature and energy as well as pressure also affect what phase you are actually going to be in. So let's go ahead and let's discuss energy a little bit before we move on to the details of the heating and cooling curves. So energy obviously is going to be directly related to our temperature and phases. Okay, so some new terms that we need to get used to are heat of fusion or enthalpy of fusion, heat of vaporization or enthalpy of vaporization, and heat of sublimation to a lesser degree. So what these actually are representing the energy that's being put in to exact a phase change. Okay, so when I am going, or when we are taking a substance and we are going from a solid to a liquid, that process is called melting, right? Okay, now the enthalpy change associated with that process is called the enthalpy of fusion or the heat of fusion. Okay, and basically this is an endothermic process. We have to add energy into the solid in order to get it to go to the liquid phase. Okay, in that same way, the vaporization process, basically going from a liquid to a gas, that's known as the enthalpy of vaporization or the heat of vaporization, right? So that's the energy that I'm putting in order to go from a liquid to gas. Okay, and in the same thought process, sublimation, okay, the enthalpy of sublimation or the heat of sublimation is related to the change from a solid directly to the gas without going through that liquid phase. Okay, so all three of these examples are endothermic processes. We have to put energy in order to get our solid or liquid to change into the other phase of matter. Okay, so now that we've identified what these values mean, let's go ahead and look at a little bit more detailed aspect of each of these changes. Okay, so basically one of the ways that we represent changes of state are on basically a graphical setup, and they're called heating curves. Basically we take a graph of the temperature versus the amount of heat that you've put into a specific substance, and it shows, I guess, the process of going from, say, a solid all the way up to a gas, or from a liquid to a gas. That's an example of a heating curve. And so we're going to look at the details of that, but the temperature a solid actually turns into a liquid, that's known as your melting point. Okay, and the energy required to accomplish that change is known as your enthalpy of fusion. Okay, so notice the melting point is associated with the actual temperature. Okay, the actual process of melting is associated with an energy change, which is related to the heat of fusion. Okay, this same thought process applies to boiling point. So boiling point is the temperature at which a liquid becomes a gas. Okay, and the energy required to make this happen is known as the enthalpy of vaporization or the heat of vaporization. So as we move on and look at the heating and cooling curves, we're going to be referring to these various melting points, boiling points, enthalpy of fusion, enthalpy of vaporization, and I want you guys to be able to differentiate between what I'm meaning by each of these definitions. Okay, so let's go ahead and let's look at an actual heating curve. Okay, so what I want you to notice about the heating curve is along this x-axis down here, we are representing this with heat added. Okay, so sometimes it's just shown as time as well, okay, and the implication is that we're adding heat during that time process, okay. However, usually along the x-axis it actually says heat added, okay. Along this y-axis here we have temperature, okay, and so now that we look at both of these, x and y axes, we can kind of look at what's happening along this curve and help us identify what's physically happening at each change process. Okay, so what I want you guys to notice about the heating and cooling curve is that, okay, besides the x and y axis, we have different areas. We have sloped lines, and then we have lines that have plateaus. Okay, so these sloped lines, all these lines with basically, you know, non-flat slopes, okay, they all represent the actual phases of matter. So in this case, because we're dealing with ice, this is our solid. Okay, here's water. That's our liquid phase, and then here's the steam, which is referring to our gas phase. So along the sloped lines, that's on a heating curve, that is representing the state of matter that you're currently observing. Okay, now at these plateaus, this is where phase changes are occurring. Okay, so phase change, right? Okay, so the phase changes are happening along the plateau. So let's talk about what's happening in terms of the energy we're adding and why the slopes are different at different processes. Okay, so guys, when we are adding heat to a block of ice or to, a beaker full of water, okay, what is happening is that we are taking molecules that are in close proximity to each other and are just kind of sitting there vibrating, and we're adding more and more heat. Okay, so as we add heat to the ice, what happens is that the molecules vibrate more quickly. Okay, they vibrate more quickly and they subsequently bump into that thermometer more because they have more kinetic energy. Okay, so remember that your temperature is the measure of your average kinetic energy of a sample. So as we add heat to this ice, what we do is we increase the kinetic energy and we subsequently increase the temperature. So the energy being added is used to increase the kinetic energy, okay, of the substance. Okay, and this is true at, as we're heating water, okay, and even when we're heating up the steam, right? Okay, so we're increasing our kinetic energy. Those molecules are moving faster, so we see an increase in the temperature, and subsequently we have a sloped line. However, when we get to the phase change, that plateau that forms basically is indicating that something else is happening. So in this case, guys, notice I'm still adding heat along this plateau, right? Okay, I'm still adding energy. I'm still adding joules of energy. Same thing is happening here along this plateau of this curve. Okay, so during the phase change, right, I have no sloped line. I have no increase in temperature. So it's not my kinetic energy at this point that is increasing. What's actually happening is that the energy that's being added is being used to increase the spacing of the particles. Okay, so what I'm doing is the energy that goes in is increasing the potential energy, or that spacing of the particles within that sample. So as I'm putting the energy in to pull apart those ice particles and put them into the liquid phase, okay, the energy that's being put in is being used to directly cause that separation. Okay, it's not being used to make the molecules move faster. Kinetic energy is not changing. Potential energy is what's increasing. Okay, and that same thing is true for the process of going from, water to steam. Same thought process. I'm pulling those particles farther apart. There is no increase in temperature, so there's no increase in kinetic energy, and I'm subsequently seeing the phase change. Okay, so the phase change, okay, that melting point or that boiling point, those temperatures are constant. So that's why we refer to, our boiling point or our freezing point, however you want to look at it, as specific numerical values, because there will be no temperature change over that melting or over that vaporization process. Okay, it occurs at constant temperature because all the heat that's being added is being put in to pulling those molecules farther apart. Okay, so once again, basically that melting point, that numerical value that we were talking about in terms of our temperature, that's referring to the heat that's being added in order to make the molecules move more rapidly. Now, once we get to the actual melting point, we're not making them move any more rapidly. The energy that we're adding is just making them move farther apart. Okay, so the melting point is going to be that that temperature value associated with that phase change process. Okay, so basically the energy that we're referring to that's being added to the substance at its melting point is called the heat of fusion. Okay, and that temperature value is going to be that melting point. So please differentiate between the two. One is referring to the energy required to make the change, okay, which is referring to our enthalpy or heat of fusion. Okay, and the melting point is the temperature at which this change occurs. Now, the boiling point, guys, is a little bit more complicated. Same thought process in terms of, heat of vaporization is the energy that's being added during that phase change, and your boiling point is the temperature at which that change is occurring. Okay, now boiling point is going to happen when the vapor pressure equals the external pressure that's being applied to the sample. Okay, so what do I mean by that? Basically, what happens is as you heat a substance or as energy is inputted into a substance, basically particles in the liquid phase are going to leave the liquid phase and enter the gas phase, right? Okay, and eventually a bunch of the gas particles are going to build up above the surface of the liquid, okay? And when that vapor pressure that's exerted by the gaseous particles that are above the liquid is equal to the external pressure, so usually atmospheric pressure, okay, that's when boiling is going to occur, okay? And at normal boiling point, that's going to happen at 1 atm pressure, 1 atmosphere. So basically I put, water on a stove and I'm going to boil some noodles. Okay, well, when I get that water to boil, we consider it normal boiling point because I'm at basically 1 atmosphere of pressure. Okay, basically superheating occurs, okay, when you're heating above the normal boiling point. Okay, and basically that usually is accompanied by pressure changes. Okay, and supercooling is, similar thought process. Okay, it's just we're dealing with cooling at a temperature below freezing point. So obviously pressure is usually involved in these processes, okay, but hopefully you understand that vapor pressure is associated with the boiling point and what actually physically has to happen to the vapor pressure exerted by these particles hanging out versus the atmospheric pressure that's being applied to the liquid itself. Now, I also want to bring you guys back to the fact that basically this vapor pressure can be associated with vaporization or evaporation. Okay, so remember, vaporization is the change from liquid to gas at boiling point. So basically we're adding heat in very large quantities, as we see on the heating and cooling curve. Okay, so but vapor pressure can also build up through the evaporation process. Okay, remember that some liquids are able to basically evaporate. We talked about like perfume, things of that sort. Okay, and this process occurs below the boiling point. So we're going to just make sure that we're keeping that in mind whenever we're talking about things. If I say evaporation, I'm meaning something different than vaporization. However, both of them will be putting particles into basically the container, right? It's going to be putting gas particles into that above that liquid layer and subsequently going to give you a vapor pressure. So please be sure that you're okay with both definitions and that you're familiar with the fact that both of them are producing gas particles above a liquid. Okay, so I do want to talk about something called dynamic equilibrium. So what do I mean by that? Okay, so dynamic, we're thinking like motion, movements. Okay, and equilibrium is basically when two processes that are the reverse of each other are occurring at the same time. Okay, so if I were to take particles that are, or if I were to take a liquid that has the ability to vaporize and put a cork into the container that they're in, what's going to happen is that the molecules of gas are going to escape the surface of the liquid and basically start to build up above the liquid. Okay, and eventually the molecules are going to build up to a certain concentration. Okay, and once that concentration is reached, okay, what's going to happen is that some of the particles are going to start to condense back down into the liquid phase. So what's physically happening here is that some of the molecules are vaporizing, some of them are condensing. Okay, and so in this process, eventually equilibrium is going to be reached. And basically, equilibrium is going to be reached when the rate of your vaporization is equal to the rate of your condensation. Now, this process can't occur if the system is open. So basically, you're not going to have that buildup of the vapor in the container if it's escaping into the atmosphere. Okay, so the fact that these molecules are constantly changing phase is where we get the dynamic portion of dynamic equilibrium. Okay, and the fact that the total amount of liquid and vapor in that container remain the same is what causes us to call it an equilibrium. So dynamic equilibrium basically forms when you have two reversible processes or two of the opposite processes occurring at the same time while maintaining the same, or not equal concentrations, but the constant concentrations of both the liquid and vapor phases. So really quickly, I want to look at condensation and freezing. Basically, we've been talking about the endothermic processes, the vaporization, the melting, etc. processes. Okay, so condensation and freezing are basically just the opposite processes of what we've been talking about. And what you need to understand with these is that the enthalpy of condensation, the enthalpy of freezing, they're going to be equal in magnitude, but opposite in sign of the vaporization and fusion processes. Okay, so basically we're losing heat in order to condense down back to a liquid. Or we're losing heat in order to freeze our liquid into a solid. Okay, and that change is going to take the same amount of energy. It's just that energy has to be lost in this process. Okay, so I guess think about the signs, think about the heat loss and gain when you're comparing these two processes. So critical temperature and pressure, basically your critical temperature is the highest temperature a substance is able to reach and still be a liquid, okay? And basically critical pressure is related to the critical temperature in that that is the pressure that's required to bring about the liquefaction process at critical temperature. Okay, so kind of they're usually related or discussed in tandem. Okay, so if you go past critical temperature, basically the kinetic energy of the particles is so high that you totally, knock out all the intermolecular forces, and it doesn't really matter what pressure you exert. You're just basically beyond any ability to keep it into the liquid phase. Okay, and different substances are going to have different critical temperatures and pressures. So if we look here, nitrogen, okay, here's its critical pressure and temperature, and water, here's its critical temperature and pressure. Now, obviously, we can look at the intermolecular forces associated with these. You would anticipate, having higher intermolecular forces is going to give you a higher critical temperature and pressure, which is pretty much the trend that we see here. Okay, so these are basically those maximum temperatures, maximum pressures that you can have when dealing with specific substances. And this is important in an engineering sense or those types of things because, if we're dealing with large-scale quantities of a specific gas or specific liquid and we're using it for some sort of chemical reaction, we want to know at what temperature we can run a reaction or at what temperature we can process something in which it's going to stay in the phase we want it to be in, right? We don't want something to be in the gaseous phase or into the solid phase, so we have to monitor those temperatures and those pressures in order to get it into the phase we want and get maximal, product output and things of that sort. So the last thing I want to talk about here is volatility, vapor pressure, and temperature. So volatile liquids are referring to liquids that want to enter the gas phase. They want to evaporate very easily, okay? And so examples of this, something like gasoline or nail polish remover, okay? These are things where we open the container and we immediately start smelling the vapors coming off that substance. Okay, so volatile liquids, guys, they're going to evaporate more readily. And the reason why they evaporate more readily is because they have very low intermolecular forces. So the example of gasoline, for instance, there's going to be mostly London dispersion forces present in that substance. Now, if we compare that to water, okay, water has hydrogen bonding. So water has higher intermolecular forces. The gasoline has, London dispersion, lower intermolecular forces. And so if I were to take a glass of, gasoline and a glass of water and put it on my windowsill, when I come back several hours later, I'm probably going to have a whole lot less gasoline present in the glass while my water glass is probably going to remain relatively full. And that's because the low intermolecular forces of the gasoline basically leads to a high volatility. Now, the high volatility, or the ease with which it evaporates, can lead to very high vapor pressure. So basically, if you have a container, right, and you have that liquid, and basically lots of the gas particles want to go into the gas phase, they're going to produce a very high vapor pressure. Okay, and so If we increase the temperature of the container that has that liquid in it, basically we're going to have an easier time overcoming intermolecular forces. Okay, so if we have an easier time overcoming intermolecular forces, we're going to have even more vapor pressure. So basically, your volatility is related to your weakness of your intermolecular forces. The weaker they are, the more volatile you're going to be. The more volatile you're going to be, the higher the vapor pressure of that specific substance that you're going to have. And so that's going to be specific to, different types of materials. So as I said, if we're comparing gasoline, which is mostly containing London dispersion forces, versus water, the water is going to have a lower vapor pressure than the gasoline. Now remember, when vapor pressure is equal to atmospheric pressure, that's going to be the point at which, boiling can start to occur, right? A normal boiling point occurs at 1 atm. Okay, so it's pretty straightforward. We, here at basically sea level, we take our pot and we put water in it, we boil the water, we put our food in there, no big deal, it cooks. Okay, it does what it's supposed to be doing. Now, changing the external pressure is going to alter your boiling point temperature. Okay, so if I increase the external pressure, basically my boiling temperature is going to increase. So this is how pressure cookers work. So basically I increase the pressure that's being exerted on that liquid, okay, because I'm basically containing all of the gas that's being evolved, or all the vapor that's being evolved, and basically more and more energy is going to go into vaporizing those particles in the liquid phase, and your temperature is going to subsequently increase because the kinetic energy is going to increase in those particles. Now, we can see the opposite effect as well. So sometimes you may have checked the back of your box and you have different cooking directions when you're at, past a certain elevation. In terms of, the location of where you live. And we don't think about it very often living at very close to sea level, but, if we lived in, let's say, Colorado or somewhere with higher elevation, we would need to use the alternate cooking directions. And the reason why is because at higher elevations, we have less atmospheric pressure. Okay, so we have decreased the external pressure. Okay, so what ends up happening is that by decreasing the external pressure, we've made it easier for the substance that we are boiling or cooking with to basically vaporize more easily at lower vapor pressures. Okay, so basically we have to put less energy in. There has to be less kinetic energy in those particles to overcome the intermolecular forces. And subsequently, the temperature at which a substance boils is going to be lower if we have a lower external pressure. So instead of cooking your food at 100 degrees, you might only be reaching a temperature of 70 degrees before you reach that boiling point. Okay, so your vapor pressure and your boiling point, if you increase vapor pressure, you're going to increase your boiling point. If you decrease vapor pressure, you're going to decrease boiling point. Okay, and so I always think about the elevation difference and how that affects cooking, and that helps me remember these features.